Morning all. Thank you for making the effort to come out, and thank you, Ollie, for agreeing to give another talk. So yeah, welcome, and we are here. We are keen to keep in touch. We are using Mage Blue Sky now. But yeah, do follow us on social media. There is suddenly out of the woodwork. Nothing's clearly come out of the thaw now because, and as Chris just pointed out, the AWS event has just announced as well. But Women in Tech is tomorrow, along with Knots Programmers meetup at the Canal House. DevOps Knots has got their rescheduled Get Good at GitOps. That's you again. He's everywhere. DS and AI have got their monthly meetup, and John Lunn is coming to talk about Fabric deployment pipelines at East Midlands Data. Cool. We are still looking for speakers for the rest of the year. We've got next month's confirmed, yes, which I'll come to. But yes, we're very grateful that Ollie has come back. Yes, next month's teaser is putting the engineering in data engineering, continuous delivery featuring Databricks asset bundles. And yes, thank you, Ollie. We'll hand over.
You picking up audio on that?
I will. I can do, yes. Okay. If you want. Well, I'll just mute mine and then you can take over.
Right. And then I will share my screen, which is this one.
You're on live.
Hi. So, this is me. I'm Ollie Hathaway. I am one of the principal technologists here at BGSS in Nottingham. I am a technical architect, amongst many other things, including developer, do platform, do data, all the things. But one of my big passions is Golang and concurrency. I'm one of the trainers and designers of the BGSS Golang Academy. And so I've trained lots of people in using Golang. And up until relatively recently, I was on one of the kind of largest digital transformations, moving a quite colossal platform from very legacy .NET systems all into Golang for both high performance and also readability, scalability, usability, all of the abilities you could possibly have. If you go to my GitHub, I've got some Golang utils that are just like reusable patterns and fancy useful stuff on there. It is worth noting, I am not an expert on Golang. That said, I have never gone to a talk where someone has claimed to be an expert who didn't immediately try to flog you a book. And I haven't written a book on Golang, so take that as you will.
Yeah.
Yet. As soon as I write a book, I'll tell you I'm an expert in it, and then you have to go and buy the book. It's a legal obligation. So, today I'm going to talk about like what is concurrency fundamentally, and what is parallelism, because whilst the two words are often used in conjunction with one another, they're not the same. What concurrency is, so how Golang works under the hood, how it's kind of doing concurrent programming is different from traditional programming, and why we don't just use kind of traditional programming methods. But the first thing you have to think of is, why would you want to switch from using something like a Node.js application to a properly concurrent application? Well, it's going to save you a lot of money. System we're looking at was running on 432 core machines, and we managed to take that down to 8 2-core machines, just by cutting out a lot of guff, but also taking it to a much more performant framework. And this is without even doing anything fancy. This was just using the underlying power that comes with running a language that's designed for the job we're trying to do. This is not a magic bullet. It will not fix all of your problems in your life or even in your code. But for certain use cases, it has substantial advantages. It is very good for stateless microservices. If you're building a stateless microservice and you're weighing up between Java and Golang, then know that in a world of Java, specifically at Google, they brought in Golang specifically to replace Java specifically for stateless microservices. So it is custom designed for exactly that use case. It's also very good for kind of low-level programming. So anywhere where you'd write a bash script and go, this is getting out of hand, that's where you can bring it into Golang. And it's very good in that kind of situation. Also, compiles down to a single executable that is very small. This means if you put a Docker container, it is very, very small, which means for Lambdas, you have a very fast startup time. If you look at the benchmarks for Golang Lambdas against everything, it's basically there's Rust and Golang up here in terms of good, and then there's everything else is a mile below. With trailing Python and JavaScript because they are interpreted languages right at the bottom. So first up, concurrency and parallelism. They are fundamentally different things. So Go is a concurrent programming language. This means it's optimized for having lots of different tasks that do different things that need to share resources or communicate with one another. Comparatively, parallel programming is where you have a lot of the same task that needs to run independently and share resources. So graphics, anything you do on the graphics card is parallel processing because graphics cards are designed for parallel processing. Vulkan is used to, say, OpenCL here, but Vulkan has taken over OpenCL's crown, or CUDA, if you're on the NVIDIA platform, is the language and framework of choice for writing code that runs on the graphics card. Databricks, the way it works is you write your task out and it splashes that task and all of the data across a sea of CPUs. So you can have a very CPU intensive task running on a massive data set that gets broken up into separate pieces of that data set. And the trick of writing good Databricks code is that you ensure that you don't need to kind of bring everything back together until the end as much as possible, maximizing the amount of parallelism. That's a bunch of words, and I like analogies. So concurrency is like cooking a roast dinner, and parallelism is like making sandwiches on a sandwich line. So if you imagine, if you will, a bunch of people making sandwiches on a sandwich line, all of them are doing the same task. Lots and lots and lots and lots of interchangeable people. And what they need to do is they need to make sure that you've got enough stations with bread and cheese and looks like tomato. And that those people aren't constantly fighting over the same resources, but otherwise are kept out of each other's feet. And there's no dependency between any of those tasks. Like you don't have one person who goes and puts the cheese on, the next person puts tomato on, where they're waiting for one another, but instead they're all doing the same task and you manage to partition it off. If you're doing parallel programming, your main goal is how can I make sure this task does not need to communicate with any of the other tasks? Concurrency, on the other hand, is like cooking a roast dinner. So if you ever cooked a roast or watch someone cook a roast, there are a lot of moving parts. There's different kinds of vegetables need to be chopped on the chopping board. You chop your tomato, your carrots. You need to chop your what's it called? Potatoes. And so you've got two resources right there that need to share the chopping board. You need to cook your roast. You also need to cook your potatoes. They're also sharing a resource. So the potatoes are now sharing resources with carrots and with the roast. The drippings from your roast go into your gravy. That means that the gravy has a dependency on your roast. And in fact, you've got a lot of different tasks that each of them you can say to someone, can you go and chop the carrots for me, please? But even if you can split that task off, it's going to be sharing finite resources with another task, or needing to communicate with that other task, similar to the kind of gravy and drippings. So concurrency is all about breaking up your tasks into discrete chunks and saying, okay, this is how you're going to communicate with other tasks, and this is how you're going to share resources with other tasks. Now, my granny could cook an entire roast on her own, every single component. It was a sight to behold from the kitchen doorway and no closer. And so concurrency is not inherently parallel. You can have a perfect concurrent application which is only running on a single thread. It's not about splashing over as many threads as possible. On the other hand, my mum would help out sometimes. So when she wasn't looking after me and my sisters, then her and Granny would work together in unison, and they would divide up those tasks amongst themselves such that all of them would be done and they wouldn't be getting in each other's way. Because with concurrent processing, because you've sectioned off your tasks so the communications between them can happen in real time, it allows you to run those tasks on more than one thread. So parallelism, if you're only running on that one thread, it's not really parallel, it's just a big application. Concurrency, you can run it on one thread, you can run it on multiple threads. It allows you to work on multiple threads better, but mostly when you're talking about concurrency, you are talking about the idea of communication between different tasks and the sharing of resources between those. The conventional machines use OS threading. What this means is if you spin up a application or a C++ application, then it will say, I've got a process that needs to run. And it will turn to the OS and says, could you give me some runtime on the CPU, please? I would like a thread. And the OS is like, here's your thread. You can use that until I take it away from you, either because I don't like you or because you're fighting for resources with other applications on the same system. What this means is you're using OS threads, and those threads they're finite. So if you've got a 16-core machine, for example, that gives you 32 virtual threads. And with thread pooling, where the code runtime doesn't actually relinquish threads when it doesn't need them anymore, but instead says, oh, well, I'm not using that right now, so I'll use it for this other process within my application. Maybe one bit of code is waiting on a database call to come back, and another bit of code is I'll pick up because my call's come back already. It means you can go a bit further than your 32 threads, and you can practically fill about 42-ish threads. This means once you get beyond that point, you're now having to swap various executions off of your threads, and you end up spending a lot of time thrashing between various bits of code. And that costs both runtime, it costs cycles to actually switch a thread over, and it costs a chunk of memory. Plus, if you are sleeping, if your thread is waiting, then the OS, what it does is it periodically wakes up CPU, so wakes up that thread and says, are you ready to go yet? Golang is different. It's a lot more lightweight. With Golang, when it starts up, it goes and says, I would like 8 threads. And the OS is like, do you mean you've got 8 tasks to run that I can manage? And Golang says, no, I would like 8 threads. I'll deal with it, thank you. And then Golang itself has a thread scheduler. And that thread scheduler is the magic. The thread scheduler means that Golang can switch which Go routines are running and which ones are sleeping. And it can do it so much more effectively than the OS, because it can make assumptions the OS can't. It also means you can have a small amount of memory for each of those. The number Since last slide we had 42. If you want to actually like test your Golang code and see how it's doing in terms of threads, you need to be pushing it to about 100,000. Genuinely, if you're trying it with a handful of threads, say 100 concurrent routines, you're not really even tickling the CPU. In fact, one of the trouble with benchmarking or with Golang is often the application that's doing the benchmarking is consuming more CPU resource than the Golang code itself. So each of these Go routines has 4K of memory. That is incredibly cheap. That means that if you spin up another Go routine, that's just another 4K of memory. It almost free. And so whereas in something like C# or Java, you'll only spin up a new thread if you really need to, or if you're using the async await pattern. But generally, you try to keep your multi-threading as low as possible. In Golang, you're like, I need to do something. I don't need to know the answer right now. I'll run it in a Go routine. And I've periodically, I've got 2-line Go routines where one of them is it's waiting for a call, and then as soon as it gets that call, it does a thing. And that's the entire Go routine. So 100,000, easy. Of course, we found out in some projects, 20 million is a lot. So if we found that if you were to run, say, 10 million concurrent Go routines, then that 4K of memory suddenly starts becoming relevant. And 4K of memory at 10 million, that is 40 gigs of memory. And you start running out of memory on servers. So unbounded concurrency, where you are just everything's a Go routine all of the time, that can get out of hand. But in terms of stateless microservices, every call that comes in, that is a Go routine. And so you can handle a lot of inbound traffic at the same time without ever worrying about running out of resources, and only worrying about the amount of CPU time your actual calls actually consume. As a side note, this is not what you get if you Google computer mouse. So, as I said, you can configure the number of OS threads that you give your application. So before, when I said I would like 8 threads, you can say I would like 1 thread. This means if you're running in something like Docker, then I mean, at that point, you're limited by the resources Docker has provided to it. And you said, yeah, I've got, 4 cores worth of power going into this Docker container, truly staggering quantity. But if you're running on your desktop, then you can say, when you run, I would like you to run with only 2 threads, please, because I'd like to give you artificial constraints. So it looks like you're running in a Docker container when actually you're running on my beast of a laptop that can handle everything. At which point you can have multiple applications running at the same time and not worrying that they're going to start fighting each other for resources and throwing off all your benchmarking. Channels are a big part of Golang. It is primarily for communicating between Go routines. This quote at the bottom is one of the fundamental principles of Golang, which is share memory by communicating, don't communicate by sharing memory. So sharing memory by communication would be if I am doing some work on a thing and then tell you it's time for you to do some work on the thing, then I would send you a message along a channel. That's sharing memory by communicating. Communicating by sharing memory would be if I have taken a lock on that resource and you are waiting for that lock to be released. Communicating between various threads can melt your brain a bit. It's why the actor pattern is very common in Golang applications, where you say, we're going to have this one resource being owned by this one thread. that will be and then we'll communicate with that thread and tell it what we want to do with the resource, and you communicate from various points, and then you only have one thread that is operating on that, and you completely eliminate all race conditions, and it means you don't have to worry about massive lock contentions. You just have to worry about the size of your buffer. It's not perfect for things where you might have find optimization with a read-write lock, but it is good for where you say, okay, I want to have a massive amount of Go routines all trying to work on the same, say, buffer or cache, and it's commonly used in caching strategies. Everyone, when they start writing Go, builds something incredibly complex. It is very easy to give in to the siren song of elegance with Go. It lends itself to looping and recursive complexity very, very well. You can say everything is a Go routine, which, as long as you're not having all of your Go routines spin off all the Go routines, you won't hit the maximum, but it becomes a bit difficult to follow. And you end up with some absolutely mind-bendingly complicated code that no one can follow, including you the following morning when you're like, what is this? And of course, when you're trying to find out where your race condition is, and you've got Go routine splashed all over the place, it becomes a bit of a nightmare. What we commonly do is concentrate all of the complex concurrency into a single area. So you know that if you're seeing race conditions, that's where it's going to be, rather than kind of splashing them across your entire application. This lends itself to if you have used like N-tier pattern design patterns, where you've got one layer that's responsible for just dealing with the HTTP handlers in and out, one layer that's responsible for CRUD and dealing with databases or dealing with writing. Then you might have in your service layer in the middle, you say, this is where the magic happens, rather than splashing it across all areas. This is just a way of concentrating all of the, what the hell am I doing, into one place to really help your brain to pick it apart when it comes to it later. So locking is a contentious issue within Golang. There's some people who still think that locks are nowhere near as efficient in use as using a Go routine. Locking, the performance of the locking module of mutex has improved a lot, but there's still very much a philosophy, which is if your first recourse is to a mutex or a lock, then you're probably thinking about your problem wrong. There are times when you'll say, yeah, actually, no, a lock isn't exactly the right thing to use here. The gRPC framework has built into it locking, because that is the correct tool for that particular job. But if you come from a C# or Java background, and you're like, oh, I've got this common resource, I'll just wrap it in a lock and reflexively use a lock, you're probably going about things the wrong way. And this is where you will find Golang is a very opinionated language, and the people who write it are very opinionated, because it was explicitly designed as a counterpoint to the object-oriented monolithic style of Java. And so it is, like Canada and the US, everything that they're not. And locking is a good example of that. So no functionality of Golang is illegal and not allowed to be used, but a lot of the functionality that enables things like locking, things like object-oriented programming, are things which you should only reach for when you know you need them, rather than reaching for them reflexively, because that's what you know how to do. So, as I was saying, Golang is really, really good for stateless microservices with high throughput. like really good at it. One of the advantages of Golang is that it builds down to a single executable. No DLLs, no extra fluff. If you are running it with it serving up HTTP content, you might think, oh, so it compiles down to an executable with a bunch of HTTP sat next to it. No, you can embed your code, your files into the executable binary. Side note, I've never run Golang as a web server because Nginx exists and tools exist for that exact job. But I would 100% have an about page that if you just hit the about endpoint, it serves you static file, or a stats page, which if you hit it, rather than just providing you with the JSON that's pulled by your metric scraper, it will actually present it in a nice fashion, or give you a button that you can click on that would reset the cache. And those kind of times you're like, oh yeah, actually, let's throw in some CSS, let's throw in some HTML, maybe even some JavaScript if you're feeling funky, but let's just create a nice little static page, which we can use to throw data on, and then embed those files within the executable. And that embedding in the executable and that having a single executable, especially a very, very small one, because it compiles down to machine code, and doesn't need to have like a JVM or a pip or the CLR in C#, means that you can put it in a Scratch container. You can put it in a container, that, a Docker container that does not need to have permissions to access the underlying file system, or even have a file system, really. It allows, so effectively, when you build a Docker container for Golang, it builds much smaller than the same application in other languages, because it doesn't need a lot of the guff that the OS generally provides. Smaller containers means faster boot time for Kubernetes and Lambda. And yeah, like I said, it's optimized for high throughput microservices. So if you're thinking of building something like this, then Golang might actually be a good choice. It's not suited for monoliths very well. So the Golang programming paradigm explicitly says don't do object-oriented programming. Object-oriented programming came about in order for people to be able to fit monoliths into their heads. Probably not literally, or hopefully not literally. But a monolith has a lot of code in it, and it's difficult to fit every line of code in your head. So what you do is you say, okay, I'm going to compile these into thought-shaped things where the actions and the data for the thing is associated with the thing, and I can now process it as a human would, as if it wasn't a bunch of code, and you end up with objects and reusable patterns. And this allows you to fit massive monoliths into your head by abstraction. Golang, small services, you can fit every line of code into your head. And that means if you add in abstraction, then you are only giving yourself a whole lot of headaches when you could just say, look, you've got two endpoints and both of them call the database. Why have you got 6 layers of abstraction within this single application? There's not even any business logic. Dependency injection, what are you injecting? You shouldn't be injecting that into yourself. This is an actual code base I was actually looking at yesterday, where someone had put 6 layers of abstraction into a C# microservice, and all it did was take the input, didn't even parse it, and wrote it into MongoDB. And I was like, that could have been 5 lines of code. In Golang, if you're writing that, yeah, that's 5 lines of code. There's no performance gain for Golang if you're writing a monolith as well. If you were writing something like an all singing, all dancing front end, monoliths get a bad rap, but there are some monoliths I absolutely love, like Elden Ring. Computer games are monoliths; they always will be. A lot of our world, still revolves around monolithic applications, and it's a perfectly good design pattern if what you need is a single application. And if you're doing that, don't write it in Go. You'll find your life is a lot easier if you write it in a language that is good for monoliths. And also, the MVC framework for .NET is really good. There's nothing like that in Golang, and if someone tries to bring that out, then it will be a poor imitation. Just go with what works for the job. Debugging in a multi-threaded environment is not simple. If you run a debugger and you've got breakpoints that are on multiple threads, it starts looking weird because you take a single step and you skip from one thread to another. Human brains are single-threaded in terms of what's going on, and it's very easy to become confused as to whether the thread scheduler has decided, oh, it's time for that thread to execute its next step, or whether it's like, actually, that next step was waiting for the previous step. It means that these things aren't working the way you'd expect. There are tools for it. I use print statements. Like, genuinely, it is quite often the best way of doing it. But the unit testing framework for Golang is built into the language. Like, not just like, oh, it comes packaged with a unit testing tool. No, if you write a code file, so main.go, then you put next to it main_test.go. The Golang compiler knows that is a test file without any other tagging. It will not compile that code at runtime. And if you say go test, then it will say, I've seen your test files. They're here. I'll run all the tests within them. And yeah, unit testing within Golang is just so much easier than in other languages, just on the basis of you're not trying to learn an additional tool chain. It comes with it. Race conditions suck. Switching, so thread switching between anything with an atomic operation has to be assumed. When I started writing Go, I would write things like, if this value is not equal to true, set it to true. And thinking, oh, that's going to catch the thing. That's going to allow me to have fencing and gating. I don't need a lock for that. I'll check and see if it's true. And then if it's not, I will deal with it. But between that if statement and the following line of code, your thread can be descheduled and another thread come in. And not even between two lines of code. If you write an update statement for a value, like counter plus plus, counter plus plus is not an atomic operation. Counter plus plus is two operations. It is, what is the counter? And then write to the counter plus one. And your thread can be descheduled between those two calls. So if you run 1,000 threads that all just do counter plus plus, the end result will not be 1,000. It might be most of the time, but sooner or later it won't be. And hopefully that's not in prod. So you can use a race flag in your tests to say, test this, try to force race conditions. But really you need to think about race conditions as you're writing your code and at every step. And that's part of the whole, let's go and concentrate all of our concurrency bullshit into one place. Learning to analyze your code is an important part of Golang. So there are tools and there are ways of doing things that allow you to dig into what is your code fundamentally doing. When I would write C# and when I'd write JavaScript things, I would say, I have tried my best to make sure that this is the most performant code that I can write. Like, I can't think of a better way of writing this, therefore it is the most performant code that can be written, that can be read by other humans. Which is fine for a lot of applications. Most of the time, we're not dealing with high performance programming. With Golang, it's like, actually, I need to see if I can shave another nanosecond off of this application call. And yeah, the profilers, and if you benchmark things, you are looking at microseconds and nanoseconds in terms of operation times. I had one of my colleagues was working on a some part of the JSON deserializer, and the tech lead who owned that part of the project said, well, you need to run these benchmarks, and the benchmarks will benchmark each of those deserializer operations to the nearest nanosecond. And if you've added a nanosecond, then you're not getting merged, kind of thing. pprof pprof is the Golang profiling tool. It's part of the Golang toolchain. It is all but built into the language, and allows you to kind of analyze your code, and it gives you nice pretty printouts and said, this is where you're actually spending all of your time. If you've ever gone and use SQL Server Profiler, it's similar to that. You can see where your bottlenecks are, see which bits of your code are actually taking the time up, rather than just going, I know what I'm doing, and this is the best I can do. Escape analysis is also big, important. This is where you try and work out, is anything escaping from the stack to the heap? The execution frame for a single thread, basically all the values that it writes and uses in memory, they're all on the stack, until it can no longer put them on the stack because you're overwriting the bit of memory that it was using, and it's a pointer, and you're like, okay, well, we need that pointer value to be, not overwritten, and so it slaps it on the heap, which means it can be used by everyone. But if it's only used by you, that pointer is not going away anywhere, and you start to fill up the memory. And garbage collector is a brutal mistress. If you're writing high performance code, which has which individual threads are going to allow things to escape from the stack to the heap, then sooner or later you're going to fill up your memory. And if you're writing really fast stuff, as we were on one project, you can end up doing a 3-second garbage collection cycle every 7 seconds, and that is all of your performance is just gone. Escape analysis is basically the process of figuring out, is the compiler going to have this pointer escape to the heap, or is it okay, and how do I make sure it doesn't get out? If you're going to drive a race car, understand what's under the hood. Any questions?
Given the optimization that you've just talked about, how much use of other people's libraries do you find in Golang? Is there a temptation to just write it yourself because you get better and faster?
Short answer, yes. So if you come from a JavaScript background, then when you need to add one to a variable, you import the add one library from GitHub, and everything's another library. In Golang, that is not the case. So firstly, the core tools, the core language has pretty much all the functionality you will ever need. And that is mostly because Golang has a niche, and that niche is very, very well filled by the core library, and is a much richer feature set than you will find in other languages. As such, when you find yourself straying outside the core library, it's for a handful of reasons. One of them is because you're trying to integrate with Kafka. And I have gone through 3 Kafka libraries to try and see if there's any code that I could just steal so I can have a Kafka emulator. And my God, no, there is not. It is colossal, the amount of effort that is required to just talk to Apache Kafka, because it's not an HTTP kind of connection you got going there. At that point, you're like, no, actually, I'm going to go out to this library that someone out there has been professionally written by, much smarter people than me. It's why we don't try and rewrite React. We just use it. But when you're looking at, say, caching, there you might go, actually, this caching library has a usage pattern that matches mine, and someone's put a lot of effort into optimizing that. But for everything else, rolling your own code in Golang is often the best way. Usually because they're trying to make something generic and flexible, and you need something that just does this one thing. Think of having Golang like having a 3D printer. You're not 3D printing a chair, but when you got that little widget to stop your cabinet from clicking every time you close it, you're not going to IKEA and then botching something together. You're printing it yourself. Check and see if we've got any questions on the call. Chat. Nope, we're all good. Cool. Thank you very much for coming. There is still breakfast things. I shall be loitering around, and you can ask me to pontificate greatly about Golang further, or other concurrency things, or what my impressions of Rust are, which maybe I'll give that talk next year. But thank you all very much for coming.